Okay, let's kind of review what we learned about energy and like how we do rotational energy in the problems as well. So I'm gonna quickly review this. So the energy conservation or conservation of energy, right? We usually say this is like CO, conservation of energy, COE. The equation is given as delta K R. Now we added that term, right? Plus delta KT plus delta UG plus delta UE plus delta I plus delta IF. And this is the final version in this class, okay? And you make these equal to work done plus heat. Okay, so we are gonna kind of briefly go over what they are and how we are going to interpret in the rotational motion. So if the object is rolling, okay, then and if it has a mass, then it will have moment of inertia and it will have angular velocity. Okay, so you need to consider keeping rotational kinetic energy. And the definitions of these are rotational kinetic energy is 1/2 I omega square. I is the moment of inertia, omega is the angular velocity. Translational kinetic energy is, moment of inertia becomes mass, angular velocity becomes linear velocity, right? Very similar form. And the once again, we'll start learning these in chapter 7. UG, gravitational potential energy, is in the form of mgy. And the elastic potential energy is in the form of 1/2 k x squared. Remember, k is the spring constant, x is the it's measured from the relaxed position, stretch or compress the distance. And I is the internal energy. We don't really have a specific equation for that, but IF, and it's specifically delta IF, is Fk times d. So this is only true if you have kinetic friction. Okay, if it is a static friction, this term goes away as well because the static friction does not do work, and there's d is simply 0 for static. Okay, and once again for the work term we did focus on the free body diagram and look at all the forces, and we will still do that. And heat transfer in this class is 0. And again, so in this class is really default is these two are always 0. Okay, later on you will add more stuff in future classes, so that's why it's important to see the whole picture now. Later on it won't be like surprise. Okay, so again, our focus in this chapter and today also is going to be that rotational, and the rest is kind of what we already know from earlier chapters. Okay, so when we do rotational stuff, again, you need to make sure that object is rolling. Okay, and then you will consider this. And another thing is, if the moment of inertia is not given, probably the mass of the object will be given, you need to figure out what type of inertia you have. And you will find the center of mass inertias from table 10.2 from Wiley Plus. It is already also provided to you on the class pages. I've been adding it for the every class since last 2 classes or so. So you don't need to memorize these. You just need to see, okay, I have a solid disk rotating around its center, then I'm going to use the center of mass inertia for the disk, okay? Or maybe I have a solid sphere, or maybe hollow sphere, or maybe cylinder, hollow cylinder or something. So you need to check what you have. That's very important. And you just need to refer to table 10 too. If most of the time, if you're not really looking for inertia, but you need to use inertia to figure out some other stuff, so that probably will come from table 10 too. The equation sheet, I want to also hopefully clear this up. Equation sheet is giving you this. This is only true if it is a point mass. Okay, if you have a solid cylinder, sphere or something, this is not gonna work. Be careful with that. So for any other shapes, you have to refer to table 10.2. But if it's a point mass, this is what you have, and this is not in the table 10.2. There is a hoop for in table 10.2. It's the first thing on this table. It is also mr square. They happen to be the same, but that is not really the point mass. That's like hoop and point mass have the same form of inertia, but the rest have different forms, and most of the time the coefficient of mr square changes. Okay, so you need to be careful of choosing which one is your case. And another key thing when you apply center of, conservation of energy in the combined motion, you will probably have both of these two, and it will look like maybe like you have two unknowns or something, like because there are two different velocities. But most of the time, what you need to use is the v is equal to omega r equation. Okay, so this is the center of mass velocity, so you can use that to figure out like related to omega, or write omega from this in terms of the v, right? And then plug it in here so that you can make them look the same. Okay, that's another key thing. Otherwise, you may get lost. And I was like, I have too many unknowns, but not enough equations, because you will have only one equation, as you can see, center of, the conservation of energy equation. So those are the things that will be clear to you once you do enough enough exercises. Okay, so we are we already done some examples. Today there's another example, and I've added 5 more problems, and there was that Indiana Jones problem. Hopefully you solved it. Solution will be available today. So please take a look at those and see how we include those in the problems. Okay.